Thank you very much, Brian. It's good to speak here. We've been at this for quite a while, and so we're going to talk about, similar to Judd, engineering with plants. And I'm an engineer. I think there's about 3 or 4 engineers in the room. We're a poorly represented group about the removal of pollutants, and we'll get on with it. But the big idea is every drop of water passes within the thickness of your finger of a root. You've got to keep that in mind, because that really is a key piece in the ground and in water. We've been at this. This is 1988. I was planting my first tree riparian buffer, and the bottom line is that, oh, that's how that works. Okay. But we need to look in terms of a reactor. We're not thinking reactor numbers, reactor functions here. We need to think in terms of a reactor. Ultimately, if the regulators want it, they normally think in terms of a reactor. And the bottom line is it's predictable, because you can control the root depth. If you take an 8-foot tree and stick it in the ground 6 feet, you can get a 6-foot deep root zone. And it's an attached growth reactor. The microbes growing on that root, which is being fed by atmospheric carbon through photosynthesis down the phloem, out through exudates and the root mass itself, is feeding that microbe, and you get more microbial activity per centimeter of soil than without roots. 10,000 times more. You get more diversity, more population throughout that root system. And this is a fast root system. There we go. This is a 19-month-old tree growing in Wyoming, fed by coal tar methane water, and this was a stick, 12-foot tree, 6 feet in the ground, and this is what you get. So we're not needing to wait around a long time. This is very important if you have a site that's really has the meter running. And we talk about pumping water. And the good news about pumping water, as you saw in that data from Hayden Prairie, it's a substantial amount of water compared to low-growing plants. You have that big leaf hanging up in the above the ground, a leaf area ratio of 5 acres of leaves per acre of soil or more, and that is pumping water, no doubt about it. And this is some of Jason Smethrude's data for, I believe, it was in Oregon, I believe, probably in McMinnville landfill, but it gains capacity. Very few systems gain in capacity with time. The Poplar, until you get to canopy, you're gaining capacity for pumping water. Oops. Okay. What? Oh. Sorry. Where the heck is this escape? Oh, here it is. Okay. Sorry about that. And this is important. This is a concept. That water is an unregulated discharge. And if you have an NPDES permit, you have to account for the water and its quality. The water that leaves through that leaf stomate is an unregulated discharge. This is a real important concept when water is what you're moving. And most of the data is well-proven. It's well-proven data. The Western Fertilizer Handbook in 1988, we still use it. We have a great biomass resource, thank you to Greenwood and all the shoulders of giants we stand on that go way back. And that gives us some resources, and this is like the Model T. Imagine when this thing becomes the Corvette, what we will be able to do with the basic material. But again, we're increasing the pollutant removal reactions by the microbes, the exudates, the plant enzymes. Things are happening inside the plant as well as outside the plant. Ultimately, a increased pollution reactant rate. Denitrification, well proven. You can fluctuate the redox potential. You can have more oxygen and less oxygen. Exactly what you want for nitrification, denitrification. Excuse me. Organics, we've talked about pathogens and pharmaceuticals, etc. Well proven that you can get a reaction rate both by adsorption things stick, and then it breaks down thanks to the microbes in a fluctuating water table. And this is important. Those Salicaceae plants are capable of being able to handle this water table. This is in Iowa. This is where it's at. Sometimes it's above the surface. The trees live. You're changing the redox potential. Chlorinateds go away in anoxic, anaerobic conditions. The carbon-carbon bonds break down in oxidizing conditions. It just gives us more treatment capacity. The amount of research already accomplished is significant for very specific compounds, many of which show up on our sites. And they're in over 400 installations all around the United States. And there's going to be more and more coming. But bottom line is you see things that are in all of our communities, coast to coast around the world. This is where our sites are. We've had the opportunity to work in 37 different states. Our biggest products right now are on landfills, and there's reasons for that. And thank you to this discussion that we're continuing today. It is a commodity, and depending on how we grow it, what's in that plant, other aspects, I mean, the nitrogen and protein concentration of a poplar leaf is equivalent to a medium quality alfalfa, for example. But there's 10,000 towns in America that have insufficient ammonia, nitrogen, and pathogen removal. And frankly, I think that this is the low-hanging fruit for we to expand our ability to use Phyto in the future in an economic way that really helps the population. And there is early data. It's like yeast, it makes the dough rise. And this is up in Coopville, Washington. And we were able to take, this is nitrate, we were able to take nitrate water, run it through these test cells that are sitting over here, and in a 3-day residence time, just virtually get complete removal of nitrate, and nitrate is hard to remove. So this is an interesting issue as it relates to Iowa and our concern for nitrate and water supplies and the whole United States and hypoxia issues. You can grow them fast, and across the United States, this is in Chicago, this is a landfill, and these are trees being drip irrigated with landfill leachate in Barrington. The bottom line is 2 million gallons a year, saves them 150,000 gallons a year, $150,000 a year, and we have 8 of these sites around the nation, and these are money-making Phyto sites. Ultimately, there's some things we're good at. Mineral solids, yeah, you capture them on the surface. Organic matter absorbs humus. Nutrients can do it. Fecal pathogens, pharmaceuticals of fat solubles we can catch. Petrochemicals, we see that. You can capture precipitate, especially the cations. You do not catch table salt. You cannot catch chlorides and many of these soluble anions especially. And ultimately, to really make a point, when you're comparing alternatives with a regulator, you need to compare against the same set of criteria. Often we don't compare point by point the same criteria. Feasible, practical, economical, safe, legal, moral, politically acceptable, and ecological. And ultimately, feasible, all the parts are there, we know how to put them together. And that is better and better with Poplar and agronomic techniques. Practical, thank you, usable by the people in the field. You do not need advanced degrees to grow trees. And in many of these small towns, they don't have advanced degrees. So we can make projects and systems usable by the people. Economical, you measure it in time, but it's time, talent, massive stuff, and efficiency of delivery. I think Poplar systems can invert the carbon footprint, not just pollute less. I think we can invert and actually have a net removal of carbon from the atmosphere and not use as much fossil carbon to make them run. Safe, acceptable for human and business health and communities. Phyto fits in small communities that are becoming economically unviable because the water treatment system uses too much money and too much energy. And there's other places too. Legal, conforming to the laws of the land. We're stuck behind the Clean Water Act. It was written in a non-Phyto era. The engineers out there designing systems are non-phyto engineers. The legal piece is really one of our biggest challenges. I think we all know that. Moral, basically giving our future generations options. Politically acceptable. I've heard last night you were mentioning the Vermont senator that basically one person can scuttle right project. And so political acceptability, we're actually pretty politically acceptable, I believe. In the new criteria for success, ecological sustainability is really a modern criteria, and ultimately, if you don't use photosynthesis, it isn't ecologically sustainable. Those are my comments, and I'll sit down so we can get on to the next.